it's just like when you have a set.
Terrific. So now you should be able to hear me. It looks like that's working okay. Good. That was very complicated. Cheyenne and Jacqueline, can you give me another thumbs up that you can hear me? Just so I'm sure that, okay, great. Okay, sorry, that was a little more complicated than I was expecting. Presenting, recording, sharing, etc. So, welcome back to in person. Yeah. So I didn't provide a link. I think what I'm going to do is put a place to put the assignments on CourseWorks. It's fine to email me this time, but I think it makes more sense for me to keep track of them there. So I'll have to go figure out how to do that. Barakit, maybe you can help me. I'm pretty sure it's straightforward, but you know. Okay, so today, I want to start by revisiting some of the stuff we did last time. Hopefully you've begun reading the Hoffman article. So we spent a fair amount of time talking about photoelectron spectroscopy. You know, I hope the point there is to give you a different angle on thinking about electronic structure of atoms and solids, how they come together, how you measure them. One of the really interesting features of photoelectron spectroscopy is that it's a surface sensitive technique because the electron can scatter. It bounces off atoms as it's leaving the crystal, or it gets absorbed again. And that changes its kinetic energy sometimes. Sometimes electrons escape without collision. And so the depth at which that photoelectron is generated impacts whether or not it's going to scatter. The deeper in the solid, the more likely it is to scatter, the less likely it is to get out cleanly. And whether it scatters depends upon its kinetic energy. Okay, so some photoelectrons are more likely to scatter than others. We saw this curve. There's a minimum in that curve. That minimum is a particular energy, kinetic energy, where the electron has the highest probability of scattering. And photoelectrons of that energy are most surface sensitive. Okay, only a few atoms at the top of the material does the electron escape cleanly. And people take advantage of this fact. They change the energy of the X-ray that's used to generate the photoelectron, and that changes how surface sensitive the measurement is, because those two different photoelectrons have different sensitivities. You can see here in this sample, a silicon substrate with all these layers on it. You see a lot more of the interior of that material when you use silver radiation that has a higher energy. The photoelectrons coming out come from deeper within the sample, okay? Whereas here, you lower the energy, the photoelectrons have less kinetic energy, they're more likely to be scattered, so you end up only seeing the top layer. Okay, so you can give somebody a substrate and they go change the X-ray energy and they'll look at how the spectrum changes and they can determine that this is surface and this is interior. Okay, that's really nice. Depth profiling is a really powerful thing to be able to do. There we go. We also talked about how you analyze the photoelectron spectrum, the ultraviolet photoelectron spectrum, to measure things like bandwidth, for example, and then a property called the work function. When you generate a photoelectron, it goes from within the material in the valence band to the vacuum level, as long as the photoelectron has enough energy, or as long as the photon has enough energy to promote that electron above the vacuum level. And there are two distances you have to worry about: the binding energy, which is the difference between the Fermi energy of the material and the level from which the electron came, and this other thing called the work function. The work function is the separation between the Fermi energy and the vacuum level. okay? So when you do this photoelectron spectroscopy measurement, what you'll find is that at some energy, you begin seeing photoelectrons produced, and that minimum energy here is referenced to 0, okay? The electrons that are highest in the solid come out the most easily because they have the lowest distance to travel. They just have to go from the very top up to the vacuum level. And then you go deeper in energy. So the electrons are becoming more and more strongly bound. You go deeper in energy, more and more photoelectrons are coming out. And then eventually, no more come out, okay? And you can't go deeper than this because below that, the X-ray you're using does not have enough energy to make this jump. From way down here, our photon energy is defined by the length of this arrow, okay? So an electron coming from this level cannot escape. Not enough energy to make it all the way to vacuum. So if you set this to 0 and you measure this, the difference between the photon energy and this energy of 16 EVs determines this value here, the work function. That's the amount on top of this depth that is going to be equal to the photon energy. Okay, Jordan?
I have a question kind of about the last slide you showed. Here we said that like binding energy, like a lower or like more deep electron would like have more binding energy, but in the previous slide we talked about how like the silicon peak is like interior.
Yes.
Is that just like different materials have different binding energies?
Sorry, I'm a little bit confused by your question. The difference between these two situations is what?
So in the slide before, like with all the layers, the interior has like a lower binding energy than the exterior.
Right. That's a consequence of the material. Sorry, I should have made that more clear. So the binding energy, this is the other way people use photoelectron spectroscopy. Silicon dioxide and elemental silicon have a different binding energy. That has nothing to do with their position. This is a reflection of the effective nuclear charge. Okay? These electrons are coming from a core orbital. The electrons in the other experiment are coming from the valence band, right around the Fermi energy. Okay? So the core, look at how much the core orbital energy changes. 4 eV or something like that, 5 eV, 6 eV. That is a difference in how positively charged that nucleus is. This is binding energy, so higher numbers to the left. These electrons are harder to pull off of the silicon atom. These electrons are easier to pull off of the silicon atom. This makes sense because oxygen is much more electron withdrawing than silicon. The substituents around this silicon atom are other silicons. The substituents around this silicon atom are oxygens. They're more electronegative. This silicon has a greater positive charge, and that means that the core level from which this electron comes is deeper by a couple of electron volts. And the nitride is intermediate. That makes sense. Nitrogen is less electronegative than oxygen. And so this energy is, it's a little bit easier to pull that core electron off of that silicon. Okay? So these differences are all just about how positively charged the silicon atom is. It's not really about covalency, there's no bonding. This is a core level that we're probing here, right? This is a 2p spectrum. Silicon's valence orbitals are 3s and 3p. So this is a core level. Okay, so that's pretty cool. You can look at the atom and say, what kind of a silicon is it? If you take a silicon wafer, you can watch it oxidize using this technique. People try and assign the oxidation state of transition metals this way. Okay. Work functions of metals are all over the place. People, when making devices, choose different metals for different applications. They want the Fermi energy of their electrode or their contact to be within the band that they're trying to add charge to or pull charge out of. That's how you get a good contact, and the voltages are matched. And so you change the material you're using. Something with a very low work function is a material whose electrons are close to vacuum. No surprise that something like cesium is going to have a very low work function. It gives up its electrons easily. These other materials, gold, that's pretty deep, 5 eV away. Surface adsorbates change these values. Okay, if you're leaving the material and there's a charge on that surface, it changes the energy it takes to get out of the crystal. Electron donating and electron withdrawing substituents modulate the work function. So work functions are not single value things. They depend upon how the crystal is terminated. Okay. So then we started talking about block functions, which are going to continue today. Remember, this is a method of generating a wave function. This is a wave function generator that uses this e to the ik business. You sum up component orbitals. These chi's are component orbitals. We're going to make linear combinations of them. The distance between the atoms that are making up our material is this value A. It's going to be our unit cell. It's the spacing here between a linear chain of hydrogen atoms, which we're using as our first wave functions. So you can get different wave functions using this block equation by changing this parameter K. Okay? N is the atom number. Now, we said e to the ikx is actually this cosine and sine function. This is a periodic function. Now, if you want to make a wave function out of using this thing, what you can do is plug and chug. And you have to remember a couple of things. E to the 0 is 1, obviously. So there are a couple of values that are easy to solve for. K equals 0 is one of those. When you do K equals 0, this is just a plus, plus, plus combination of each of these functions at each atom. Another solution is K equals pi over A. When you have K equals pi over A and you plug that in here, you end up with e to the I pi. And you have to remember that e to the I pi is equal to -1. Okay, so if you have a -1 in this position, then the sum of these things ends up looking like this. Okay, so when you have this value, K equals 0, and you have a bunch of hydrogen 1s functions, you end up with a totally symmetric combination, right? This is like, you remember a ring of p orbitals making a benzene or cyclopentadienide or an infinitely large chain. This is the all plus combination. The K equals pi over A solution is where it changes sign, right? The value of N here goes from 0 to 1 to 2 to 3 to 4, etc. And it just jumps back and forth from plus to minus to plus to minus to plus. So these values of K give wave functions that are very well defined. Now, we looked at the Frost circle. You remember the Frost circle, and we came up with this cosine function that gives you can give you the energies of each of the MOs. We can do that same sort of thing here, where e to the k is alpha plus 2 beta cosine Ka. And beta, remember, is this orbital, or 2 beta is this, beta is the orbital interaction energy. So just like in a molecular orbital diagram for benzene, the range of energies that you get for all these wave functions goes from alpha plus 2 beta to alpha minus 2 beta. And as you vary from K equals 0, which we just did for a bunch of hydrogen 1s functions, that was the all bonding combination, to the K equals pi over A, you go to the all anti-bonding combination. But if you have an infinite chain, there are many different solutions in between 0 and pi over a. Okay. And if you plot their energies like this, as you vary k, you get a function that looks like that. And if you went to higher values of k, it actually would come back down again, and then it'd go back up again and come back down again. All those other solutions are not unique. Okay, the unique solutions we're interested in are from 0 to pi over a. And each point along this line here, they are infinite, but you can imagine each one of the positions along this line is a unique molecular orbital. And it has a different nodal structure. We start from no nodes, and we go to a node between every single atom. And then there are a bunch in between, just like for benzene. Ethan?
I'm just wondering, like the way the slope of this graph looks, it looks as if they're like the states are more densely packed near 0 and pi over a.
Yes, that's true.
As opposed to the middle. Like, what are the implications of that?
I don't have a great answer for your question. I think it's a thoughtful one, but I'm not sure what to say about it. Your observation is correct, that there's a much higher density of states right here, and really at the band edges, you're more likely to see a high density of states. Okay, and that's just a consequence of what block functions look like. So for a given function, if it's a simple single orbital function defining a band, the density of states close to 0 and pi over a is higher. That's true. Okay, so this unique range of values is called a Brillouin zone. We'll see that terminology in a little more depth later. Another very important property here that defines this energy. So alpha, this is just the ionization energy of the orbital that we're making a linear combination of. That's the starting, hydrogen atom in the gas phase energy. Betas comes from the orbital overlap, and that term here, the bonding energy, contains A in it, right? That's the unit cell dimension. So if you change the unit cell dimension, you can change the energy of the overlap. Sorry, I got a little out of order. Yeah, we'll just do that first. If you change the spacing between the hydrogens, you get different bandwidths, right? These three levels have different orbital overlap, or these three different arrangements have different orbital overlap. And the spread from minus to plus 2 beta changes. So you shrink the bonds between the partners that are in the crystal, and you get a wider separation between the all bonding and all anti-bonding level. Okay, this is equivalent to saying the bandwidth is increasing. Again, though, always 0 to pi over a. All right, so the spread in energy is a function of the orbital interaction. We've talked about this basically every lecture to remind you. This width is a consequence of bonding. Now, let's talk about what this K value does for us, okay, beyond just the math of wave function generation. I think you've seen now K, one of the things is it tells you how many nodes you've got. So 0, K equals 0, no nodes, pi over a node between every atom. And this really is a measure of the symmetry of the wave function, okay? The totally symmetric combination, and this is the totally anti-symmetric combination. So it's like a symmetry index. Another way to think about this is in terms of the wavelength. So you can remember that this is a description of a wave in an electron. It has a wavelength associated with it. Same thing is true here, right? The wavelength of this wave function is much shorter than that one. So, you know, you can look at de Broglie's relationship, which relates the wavelength of an electron and its momentum. And when you talk to physicists about this, they love to talk about the momentum of the electrons in the crystal, and they're really talking about their wavelength. It's related to this vector k in the following way. So if you just take lambda equals 2 pi over k, and then you substitute in these values of k, you can see that the wavelength becomes infinitely large here when k approaches 0. And when k approaches pi over a, you get a wavelength that's twice the unit cell dimension. Okay, so this k value people talk about as something that influences the wavelength or the momentum if you're a physicist. Okay, so let's do this game again, but now we're going to use p orbitals instead of s orbitals, right? Linear combinations of p orbitals, we're going to start off with k equals 0, and we're going to do pi over a again. K equals 0 is always just a plus, 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 plus combination. So now I've taken a bunch of p orbitals and I've lined them up without changing their sign as we move from atom 0 to 1 to 2 to 3 to 4. We're going to do the same thing again. Pi over a, e to the I pi is -1. And as we go from atom 0 to 1 to 2 to 3 to 4, this thing changes sign. So our function starts off pointing this way, but on the next atom, it gets inverted, right? When you multiply this anti-symmetric function by -1, it changes. And it changes, and it changes, and it changes. So if you analyze these wave functions for a minute, you'll see that there are nodes between all of these component orbitals, whereas these ones are bonding in all cases. That's the inverse of what we saw with the hydrogen 1s functions, right? The k equals 0 solution, where the hydrogen 1s orbital doesn't, the hydrogen 1s orbitals don't change sign as you run down this wave function for k equals 0. And that means they're all bonding. So you actually get a different result when your component orbital is different. So if you do the same thing like we did before, now the k equals 0 solution is the all anti-bonding one. The pi over a solution is the all bonding one. And when you let this function vary, this cosine function, you go from high energy to low energy as you go from 0 to pi over a. So this band runs in the opposite direction. It's sort of out of phase with the s orbital combination. And that's a function, that's a consequence of the symmetry of the component orbital that we're using to make the MO. So let's take a look at this band for a second. When you go from 0 to pi over a, it starts up high in energy and goes down. That tells you it's an anti-symmetric function that's combining to make the MOs. Not the same for the hydrogens. But if you look at the energy, or if you look at the density of states diagram as a function of energy, you get something that looks like this. Here we've got the Fermi energy marked on both of these. This is just the derivative of energy with respect to k that gives us this density of states plot. This diagram tells you more than this one does, right? Most of the time we've been looking at density of states plots. We're just thinking about orbital energies, how they relate, where they are in space, how wide they are. That tells you about the bonding. This kind of a diagram tells you more than that. It has this information in it, but it also tells you about the symmetry of the function that's combining. Right? Because it starts up high and drops to low. So these sorts of diagrams contain more information than these do. Chemists tend to talk about this stuff, physicists like these ones. There's quite a bit that can be derived from these sorts of curves. Okay. All right, so I've said this a million times, one more time. The K equals 0 solution is the totally symmetric combination of component functions. That gives you an anti-bonding wave function if you're starting with P's. It gives you a bonding wave function if you're starting with S's. Pi over A is the opposite. Okay? So let's do a more complicated example. We're going to make a chain of platinum cyanides. And you guys all know the d orbital splitting diagram for platinum tetracyanide, right? So think about this. Now we're going to make a linear combination of square planar compounds. Think about the orbitals in platinum tetracyanide. You got 4 cyanides. They all point at the dx squared minus y squared orbital, right? They also point at the donut of dz squared. And then you have the xz, yz, and xy. Those are the pi symmetry orbitals. And they point at the pi stars of the cyanides. The xy one is in the plane of the cyanides. It's got 4 lobes, all bonding with all 4 cyanides. Xz and yz are above and below the plane. And they make bonds to 2 cyanides. And that gives you a d orbital splitting diagram that looks like this. There's the pi bonding level, xy orbital between the cyanides. These are also pi bonding. This level is anti-bonding with respect to the cyanides. This one is really anti-bonding with respect to the cyanides. Right? You know that. And then we have these other functions up here, pz, px, py. Px and py strongly anti-bonding with respect to the platinum or with respect to the cyanides and so on. So now if we take this component, right? This is our monomer that we're going to make into a polymer. And we're interested in analyzing how the bonding develops in that chain using this basis set. So these guys are going to overlap with each other to make the following bonds. Think about this platinum center here. This is going to be our z direction, right? dz squared. You have 2 platinums coming together, and those dz squared orbitals are pointing right at each other. We also have xz and yz pointing right at each other. This leads to sigma bonding for dz squared. The 2 d orbitals give you pi bonds, xz and yz. And then this xy and x squared minus y squared level, those guys do delta interactions. PZ and S also make sigma bonds. Okay, so you've got this chain here. These are actually really common, not this particular one, although it probably does exist to some degree. But square planar platinum compounds tend to make these chains. When they're neutral, meaning the valence is platinum 2+ in all cases, they're sort of yellow and they're insulators. But if you oxidize them, you get very colorful compounds. Okay, so why does that happen? The conductivity goes way up when you oxidize the material. In the neutral state, it's sort of an insulator or semiconductor. So let's look at these MOs. Okay, here's dz squared combinations. So this one here, the totally symmetric combination of z squared. This is the totally anti-symmetric combination of z squared. Right? This solution here, not changing sign at each position, is k equals 0. This one is changing sign at each position. That's pi over a. Let's do the same thing for xz and yz. Now we've got not changing sign. All of these are k equals 0. Not changing sign. Notice how these form anti-bonding interactions with each other. There are nodes here. This one, this is the bonding combination. This one, these are bonding interactions. This one, anti-bonding interactions. Okay, and that's a function of the symmetry of each of those orbitals. So let's take those various, let's look at each one of these energies now of our starting component orbital. So this is where dxy started, dxz and dyz started here, z squared there, and so on. And then you get linear combinations of each of those functions, giving rise to this set of E versus K lines. Notice how these three have very different widths. Right? This one is really broad, all the way from the Fermi energy down to here. This one is really narrow. That's because they have different orbital overlap. Right? A dz squared orbital, man, really good bonding. Pointing right at each other, really good anti-bond. Not so bad? Nah, you know, there's some interaction there, but it's not that significant. Okay, so when you make a band out of these components, you don't get much width at all. The other thing that happens is that this function runs up in energy as you go from 0 to pi over a. This function runs up. This one runs down. This is a sigma bonding MO. This is a delta bonding MO. This is a pi bonding MO. So the direction that it runs is a consequence of the symmetry of the interaction. No internuclear nodes, one internuclear nodes, two internuclear nodes. And that flips the sign of this E versus K. Same is true up here. This is another delta. This is a sigma. The delta runs up, and the sigma runs down. Now, does anybody want to ask any questions about this?
What does it mean that the PZ starts in the middle graph? Oh, it like is.
That's right, it's cut off.
Is that just for clarity, or it's like?
For lack of clarity, it's yeah, to spread out the rest of it. I mean, there are other levels, right? I didn't draw S on here. X and dy are not on there. Core levels are not on there. This is just windows of the energy space. Where's the HOMO-LUMO gap? Where's the band gap in this material? How do you know that?
That's the Fermi energy, and that should be the highest. Then I looked at the next highest one.
Yeah. 50% occupancy, right? Sort of the top of the electron energies. There's a spacing here. The electrons are not really populating this to any significant degree. Does that make sense? How would you know whether that makes sense? What if I didn't draw the Fermi energy on you? How would you figure out where the Fermi energy was?
I mean, you can think about, I mean, if you just look at it, like there's a pack of lines. Yeah. Looks like this, yeah.
I would like a different answer than that. I think what you're saying is reasonable, but I think more than
My answer is sort of similar, but if we know that the material is an insulator, then we should look for a Fermi energy where the gap is. Because if we knew that material was metallic, then we would know that there would have to be states at the
It's often the case that things are conductors. Like this one, for example, is a conductor when it's partially oxidized. Typically, materials like this have a dark blue color, and they're decent conductors. Okay, so if I gave you this dark blue crystal and you measured its conductivity, you'd say, oh, it's a pretty good conductor. How would you know whether it was a metal or a semiconductor? Temperature dependent measurement, that's how you would figure it out. But there's a better answer than what you guys are giving. What I'm asking you is to tell me which levels have electrons and which do not. Right? How do you know which levels have electrons? From the splitting diagram, sort of. Zuka?
I was saying, like the previous slide, you can see the highest occupied easy squared.
Yeah. So the way that I would answer this is slightly different. I would say I know the electron count of a platinum 2+. Right? Platinum tetracyanide 2- is a platinum 2 complex. And I know how many electrons are sitting on each platinum 2. 8 electrons on each platinum. And I know the orbital levels that those 8 electrons fall into because I know the d orbital splitting diagram for this compound. The d orbitals are the valence orbitals of the platinum center. There are 8 electrons in those d orbital levels. They fall into these components. So by analyzing the monomer, you could say, you know, sort of which levels are filled and which are not. And then you look at a diagram like this one, right? I could leave off these labels. You don't need those labels. You could look at that and say, oh, look at that, a W-generate high symmetry orbital or collection of orbitals. These must be sigma or delta. Look how wide this one is. Platinum tetracyanide is square planar. I pick the z direction along the chain. I'm expecting a dz squared function that makes a sigma bond along that chain. It's going to go from 0 over a. It's going to go up in energy. So you have to think about the component that makes up this polymer to analyze it. Okay. So is it a semiconductor, a semi-metal, or a metal? From this labeled thing here, yeah, this is a semiconductor. We're going to talk about this more later. I'll just say, if you oxidize this compound, this polymer, you start pulling electrons out of this. Start pulling electrons out of this band, the Fermi energy is actually going to start going down this thing. Now you end up with a system where the Fermi energy sits in the middle of the band, on the edge of it. And it becomes conductive. And it becomes metallic. You oxidize. All right. So let's do this again. But this time we're going to look at more than just 1D. We're going to look at 2D. Okay. These crystals are 3-dimensional. You make micro-orbitals or crystal orbitals in a 3-dimensional thing. Life gets more complicated. We're going to just do a square net of hydrogen. Fun fact, if you take hydrogen gas and you pressurize it to very, very high pressures, you get close packed lattices of hydrogen atoms. You get a band of orbitals, the bands that arise. It's metallic. It's So we're doing the molecular orbital diagram for such a solid right now. So when you have a two-dimensional thing like this, you have to think about the K in X and Y. So we're going to look at how the orbital function changes in both the X and Y directions. And what this reveals is that the wave functions end up having a directionality to them. You have to consider that directionality, and K becomes a vector. It's not just an index along the chain. Now it can point in different directions. So we're going to talk about its X and Y components of making up these wave functions. And the magnitude is related to the wavelength or the momentum of the electron. Pi over A, so you have directionality, and you have wavelength. So people look at the symmetry of this crystal here, and they depict it using this sort of a representation. This representation looks at wave functions that vary along this direction and this direction. So these arrows refer to the vector and its direction with respect to the crystal. So this square is oriented like this square to illustrate that we can look at wave functions along this direction and we can look at wave functions along that direction. Those are the unique directions within the crystal. Irreducible directions of the crystal. And now you end up with a diagram that looks like this. It's given these labels M and chi and gamma to illustrate the energy of orbitals as you change from, say, you go from this point toward this point, you traverse this direction in the diagram. And if you go from this point to this point, you traverse that direction in the diagram, and you get this much more complicated sort of shape. Let's just, before we figure all of that out, let's take a look at some example wave functions. One of them is where K is 0, both in the X and Y direction. Okay. So this is a vector that doesn't point, it just is represented this way. This is the gamma point where K, X and KY are both equal to 0. There's no directionality. In that case, if we take this basis function as sort of our origin, when we go along the X direction, you'll see no change in sign. That's what block function gives you when you're making a block function that changes, or with K equals 0, you don't get a change in sign. Same thing in this direction. KY is 0, the wave function is not changing sign in that direction. All right, so the gamma point in this diagram here refers to the all bonding combination of hydrogen on this one. Let's do another example to help shake that out. So here's a wave function where in the X direction, each orbital is changing sign. Plus to minus, in the X direction. In the Y direction, it's not changing sign. So Kx here is pi over A. Changing sign as you go in the X direction. Ky is 0. Here's one where they're both pi over A, changing sign in both directions. And here's the other case where X is 0 and Y is pi over A. So this M point in this lattice here, it actually refers to the orientation of the wave. Okay, so look at this one in X. This wave is sort of propagating in this direction. The nodes are all oriented in this way, so it's undulating in this direction. This one is undulating in that direction. This one in this direction. So that matches up with these arrows that you see here, right? Where K, X, and KY are pi over A, you get a wave function that orients the crystal in this manner. For X, you get a wave function that orients the crystal in that manner. So you have these lattices here, an illustration of the momentum or the orientation of the wave in the crystal against that crystal symmetry. So now think about the energy of this molecular orbital. This is an all bonding combination. And so it's going to be very low in energy. There it is, the gamma point is the lowest spot on this molecular orbital diagram. These two have the same energy, just have different orientation. They're not unique, really. And this one here is antibonding in all directions. So this M point is the highest energy point on the right. This X point is intermediate. So when you're going to look at these sorts of diagrams, you're going to see them, I like to call them spaghetti diagrams. You're going to see all these lines wobbling all over the place. And these symbols tell you about the direction of wave propagation in crystal, orientation of wave function, and how it varies in space and in energy. All right, so let's do one more example here. So we've already done these two, the chi and x point. Now we're going to look at a different value of kx. So we did pi over a this time. Now we're going to do pi over 2a. Twice the unit cell. Here's one where x is pi over 2a and y is 0. Here's one where kx and ky are pi over 2a. So this is a case where you have to go 2 values of a for the thing to go through a cycle. And in this type of a wave function, the node actually sits on the atom here. So these guys look approximately non-bonding. Same thing here. Yes, it changes sign in that direction and in that direction, but they're separated by quite a bit of space. So this is halfway from 0 to pi over a. What do I want to say about that? I guess it's I'm not going to say more about that until we get to physics. So in any case, I think, I've been hammering this in. It's a lot to take in, but K is a vector. It tells you about the direction of the solid. It's a statement about the momentum and the wavelength. Notice how the wavelength here for this pi over 2a function is different than that one. And you can analyze how energy changes with direction. Okay, so in order to we're going to do the diagram for graphene in just a second. In order to understand that, you have to think about the orbital basis set. Okay, so we've been looking at this hydrogen 1s series here. This is the pi over a. This is the pi. Pi over 2a happens to be right in the middle of this diagram, right? Halfway in between. That's kind of like the non-bonding combination. But you can also do this sort of a diagram now where your basis set is not one atom, but 2. So in this case, basis set is 2 atoms, k equals 0 is still the same. But in this case, now k equals 0 for this guy is different. So, so if this pair of atoms is your basis function, and notice you can think about this in terms of like pi bonds. Let's say we made a linear chain of pi bonds. The component function could be the pi orbital and the pi star level. Now, if you consider how the pi star level changes at k equals 0, you're going to get a situation where the sign is the same, and it's all antibonding along that chain. The k, where pi is pi over 2a, ends up looking something like this for these two. So, Hoffman says you can think about this number of bands, and you're going to see this in a lot of diagrams, where the number of bands that you see is a function of what the unit cell is, or what the orbital basis set is. Single atom basis set and the 2 atom basis set is equivalent to taking the single atom function and folding it in half on a piece of paper. So this line here is the same thing as this line. It's just folded in half. And you change your unit cell dimension or your basis set, you get this change in the way the line runs, but it's really the same line. Let's do this for graphene. So in graphene or graphite, we're going to take combinations of pi basis functions and pi star basis functions. Here's our symmetry, our lattice at the unique directions that we're going to consider. What's the gamma point? That's k equals 0, right? In x and y. And so now we're going to pick here in this crystal, this little guy, this pair. This is your orbital basis. This is the pi star basis. This is the pi basis function, right? These are wave functions for x and y, both equal to 0. For the pi set, there's no change in sign. So all of the p orbitals have the same symmetry. For the pi star set, there's no change in sign as you go from this pi star level to that one, to that one, to that one, or in that direction, same thing. Okay, so gamma point for graphite or graphene, in this analysis where we're using pi star and pi as our component, this looks like this. The M point here, starting with the blue. I always struggle with this standing in front of it at the board. Yeah. Well, I don't think I'm going to try and derive these for you right now, but bottom line is when you have, so the M point is where x and y are both pi over a, and this x point is where it's 0 and pi over a. Here for these pi and pi star functions, this guy is pi over a, and then 0 and pi over a. And you end up with a diagram that looks something like this. Now, if you were to take this guy, notice how this line and this line basically line up with each other. You can sort of imagine unfolding this diagram, just getting to the single p orbital basis, but this is how it's generally drawn in this way. Notice the Fermi energy here, marked as this dashed line. And graphite happens to fall on the K point in the diagram. Gamma point is the lowest energy function. That picture. Here's that same diagram. Now, actually, we've included the sigma basis here. So before we were just analyzing the pi symmetry orbitals, but there's also sigma symmetry orbitals that come into the mix. The Fermi energy sits exactly at that K point. Interesting thing about that is that that wave function is really, it's essentially a non-bonding orbital.
There's very little overlap between these atoms. Each of the nodes in this wave function separate the orbitals from each other. So this K point tends to be, is thought of as being a non-bounding type of function. All right, so Fermi energy tells you that the highest energy electrons in graphite sit in essentially a non-bonding orbital, which has really big consequences for graphene's properties. All right, so this gets complicated. Wow, suddenly this picture looks terrible. That happens. Many crystals have more complex symmetry than in 2 dimensions. There are 3-dimensional materials out there, and those materials have many more unique directions. When you see an E versus K diagram for those materials, you get many different points on the diagram if you wanted to analyze all possible directions. Often you just see sort of typical crystallographic orientations, the sort of lowest indice values illustrated here. But there are many different symmetry of crystal. All right, so we're going to spend a little bit of time talking about properties. Sorry, I meant to say this K point here, it turns out is really very interesting for graphene. It turns out the conductivity of graphene, the thing that physicists are really interested in, actually relates to the fact that this K, the Fermi energy, sits exactly in this K point. People often plot the various wave functions here out in X and Y. They show these diagrams illustrating what happens as Kx and Ky vary in space instead of just making a 2-dimensional representation. And this gives something people talk about as like a Fermi surface, where you get a conical intersection here. And this very point here is something I think we'll talk about in more detail next time. All right, so sorry, I wish I was a little more prepared. Better job. When you look at these diagrams, you can take away information about the symmetry of the orbitals that are combining, and that's a really very useful thing. It's related to this index K. You have to know about the block functions in order to derive those, to understand why the functions run up and run down as K varies. Remember that K is a measurement of the wavelength or the momentum of the electron, and that really says a lot about the properties of electrons that sit in those orbitals. So that K value is quite useful when thinking about the real properties, as we'll see. Remember that the width and energy is related to the orbital interaction strength. Keep saying this. Bandwidth is a very, very useful thing to look at. Is there a strong bonding or not? That has a big impact on the final material. Okay, so I think I'm going to stop there.